Indeed, impact. So I like to discuss with you how chemistry can truly contribute and even realize all our sustainability goals. And I'll focus on this topic with a holistic view, so a general systems perspective, how chemistry really can do this. And that will lead to novel research questions that I will try to develop using physical organic chemistry. So bottom-up mechanistic design, really from the molecules and materials point of view, how can you design chemistry that is then needed? So like I said, first circularity in chemistry, and then I will focus on two topics in particular using main group compounds, phosphorus, nitrogen, boron, and I focus on steric attraction, so the attractive forces which are equally important as steric hindrance. But steric attraction gets much less attention, so these are basically the attractive van der Waals forces, the picture here of van der Waals. And I will focus on single electron transfer generating radicals that can ultimately react with more inert substrates like greenhouse gases. So let's start. Let's start with the key biogenic elements, SNOPs. So carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And these elements are essential for the origin of life. These are currently 97% of all living matter on Earth is composed of these elements, so these elements are really essential. But nowadays, I actually would like to say that these elements are the origin of waste. So the reason that we do this symposium online is depicted on the left, but I like to focus now on these big waves, climate change, biodiversity loss. Which in my view are also connected to these 6 elements of the origin of life. So from a cartoon to a bit more scientific perspective, this is a paper like 6 years ago it was published, and this presents the planetary boundaries. If you look at this as planet Earth, and you think of all these aspects as being waste problems, and of course, green means okay, yellow, orange, maybe not so okay, we need some action. And if an issue is in the red, of course, it means immediate action is required. So if you look at climate change, of course, CO2 and methane in the atmosphere, and urgent action is required. And often these topics are linked. And so too much CO2 in the atmosphere causes climate change, and too much CO2 in the ocean causes ocean acidification. We'll see here that the key nutrients, so fertilizers, phosphorus, nitrogen-based components, are also entering the environment, causing damage even. So also their action is needed, and all of this is impacting, of course, the biodiversity in great deal. Now, these waste problems are basically nothing new. The impact of mankind on the phosphorus cycle in nature was already published in Nature quite a few decades ago. Climate change, the effect and the impact of coal, the burning of coal, emission of CO2 was already published in 1912 in a newspaper from New Zealand. So clearly, as these issues are still occurring, we need change. We need a radical change, because in my view, that's the only way that we actually can tackle these issues. So how to do this? And I think the concept is already there. It's the concept of the circular economy, where we're not converting resources into products only, but we design products in such a way that after use, we can actually recover them and then recycle them so that they can continuously be reused. Now, this requires, of course, novel chemistry. So this is not only focusing on resources, fossil-based or renewables, but it's truly the use of chemistry to close the cycle. And that's why, based on teaching green chemistry, we actually developed this concept of circular chemistry. Now, you can ask yourself, I mean, these guiding principles of green chemistry, are these not enough to actually contribute to sustainability also in a circular fashion? And then we thought, no, there is more needed. For example, often if I hear we use a renewable feedstock, then typically that is directly associated to sustainability. If for example, bioethanol is used, then the entire process that uses bioethanol is green, is sustainable, and so on. But I would say, in my view, this is just a different feedstock. Either for organic chemistry, you use oil, fossil-based, or you use renewables like biomass and CO2, which is an important step forward. But if you change feedstock, if you change resource, you're not necessarily solving the waste problem. And so this is the reason that companies like Avantium are now making plastics that are made from renewables, and those plastics are also recyclable. And so if you look at the green chemistry principles, we came to the conclusion that these principles greatly optimize a linear process from feedstock to product. But of course, more is needed. In a linear economy, that's enough, and then you end up with waste, products unused in the end. But of course, ultimately, we would like to develop the concept of the circular economy. Closed loop, where it not necessarily matters if you start from a fossil feedstock or a renewable one in the first cycle. The second cycle and so on starts with renewables, and that's key. And so we also would like to focus not only on resources at the start, but also at the products, because those products, they truly need to become renewable. And so if you think of the role of chemistry, from a general perspective, then of course, making molecules and materials, green chemistry is essential. And why do we make those molecules like medicines and materials like plastics? Because they have specific function, they have specific properties. And if you are remaking those molecules, so at the end, then circular chemistry comes in, where it's truly important that the design of that molecule, material, allows the molecule, the product, not being persistent in the environment and not being toxic. And so actually in chemistry, typically synthesis design used to be completely decoupled from the environmental chemistry. And if you think from a circular perspective, this is not possible anymore. We need to combine synthesis design and the environmental impact of all the molecules and materials we make. So if you think of the impact of chemistry creating a so-called non-toxic circular economy, then of course we need to design products for recycling. Think of plastics, include the additives that the product needs. These also need to be taken into account if you start recycling. But not all products are suitable for recycling. And those need to be designed in such a way that they actually degrade in the environment. I think, for example, pharmaceuticals, they need to be active in the body, but when they exit the body and enter the sewage treatment plant, they need to be decomposed as quickly as possible. And you see currently that the molecules designed for pharmaceuticals are becoming more and more persistent, so that they're stable in the body, but they also are stable in the environment, creating problems. And so this is really a conceptual view of where chemistry can truly have impact, not only focusing on resources, but also focusing on the products. And so to me, chemistry is focusing on input and output, both renewables and of course zero emission. And I think to design this machinery, to design that novel chemistry, that really is truly exciting. So, of course, looking at this picture, we need innovation, because we need to solve basically these global waste problems. If you look at ozone depletion, I would say we fixed that. You know, the depletion of the ozone layer was a major environmental problem, but we analyzed the cause and solved it. It's again in the green zone. And we should do the same for the others: carbon chemistry, nitrogen and phosphorus, as well as impact on biodiversity. So if you look at the waste end, then of course, can we use that waste, like these greenhouse gases, for example, to use as a starting point to make new molecules, CO2-based polymers, for example, convert methane into high-value molecules. So those research questions is what I like addressing in my own research. Can we use methane to make, or combine methane and CO2 to make directly acetic acid with an atom economy of 100%? Can we, for example, recover and recycling ammonia so that we don't have to make it again via the Haber-Bosch process, but that we can directly use it, reuse it, avoiding the impact on the environment, and directly reuse it again. And the same, of course, holds for phosphate, which is also what I'd like to address at the end of this presentation. I should focus on the product side, working on climate change, avoiding it. Then, of course, batteries, topic of this afternoon, as a key product for storing renewable energy. And the other is, of course, which I like to work on as well. If you think of hydrogen as an energy carrier and you wish to have a high energy density hydrogen carrier, can we design such a hydrogen carrier from organics or inorganics? And both is what I like to address in my research as well. And it can also lead to these fundamental questions like, can we bypass the Haber-Bosch process for azo compounds? Because azo compounds are really important dyes, so colorants, that typically contain 2 nitrogen atoms, but they are produced from dinitrogen. Then these nitrogens are split into ammonia, and then via a few synthetic steps, the nitrogen atoms are combined again, creating these azo compounds. So can we do this directly? So this actually leads to novel research questions. So can we do chemistry that is actually able to directly use very inert, very unreactive substrates like dinitrogen, like methane? And my approach, at least in my lab, is to use Lewis acids and Lewis bases, or in other words, electron donors and electron acceptors for that. So let's have a look. Let's have a fundamental view on dinitrogen and perhaps design a process that ultimately can benefit to reducing the nitrogen impact on the environment. So if you think of the use of dinitrogen, I mean, in the lab, we use it as a protective atmosphere. If you want to do sensitive chemistry, so molecules that can easily oxidize, then you use dinitrogen as an inert atmosphere. But why is actually dinitrogen so useful? It is a very poor Lewis acid, hence the high-lying LUMO, and it's a very poor Lewis base, hence the very low-lying HOMO. So actually, in order to do reactions with dinitrogen, you need a very strong Lewis base to react with this poor Lewis acid, or you need a very strong Lewis acid to connect it with its function as Lewis base. And at the time, I was reading some phenol cation chemistry. So actually, we did 2 computations: the geometry optimization of N2, looking at the frontier molecular orbitals, and a geometry optimization of this aryl diazonium cation and the frontier molecular orbitals. And what you can see is that if you add a phenylcation, the HOMO level is hardly unchanged, but the LUMO level is greatly stabilized. And so this means that this molecule is actually a far better Lewis acid than N2, and is also a far better electrophile in subsequent reactivity than N2. And so this could be a way to stepwise do chemistry with N2, because if this is a far better Lewis acid, and so now this is a nitrogen-based Lewis acid. Most nitrogen compounds are Lewis bases, but this is a Lewis acid, then it should be able to react with a Lewis base. So this is what we did, and this is simply from the design of the chemistry. We added a bulky phosphine, and lo and behold, the phosphine adduct to the aryl diazonium cation occurred instantly, and we also got a very nice colorful compound. Now, and interestingly, if you look at this as a ligand, phosphine ligand in catalysis, also the N-heterocyclic carbene ligands are frequently used. Typically, those are prepared and designed after the phosphine analog, but in this case, the carbene analog is already known for decades and is already commercially available. So basic red 51 is literally the N-heterocyclic carbene adduct of such an aryl diazonium cation. If you think of physical organic chemistry, of course, Hammett rules. Hammett is founding father of physical organic chemistry, and he designed principles that if you tune the para substituent, electron donating, electron withdrawing groups, you can tune the entire system. And if you, in this case, we can tune the electronics on the phosphorus center, and it's a direct correlation with the phosphorus NMR chemical shift. And we also can directly tune the color. Now, these molecules are commercially not so interesting simply because of their price. The phosphines needed in this case are simply too expensive. Because if you look on Alibaba, this compound is 1 kilo costs 10 euros, and the phosphine ligand is already more expensive. But still, it's a very nice way of making colorful compounds, and also it led to us to address again this question: why not designing this molecule directly from N2? And the same goes for, can you directly use methane as inert substrates, because both are quite unreactive. So if you look at this molecule, it's basically a Lewis base, and it's a Lewis acid, the phenylcation, and the N2 is trapped inside. And so would it be possible to design a Lewis acid and a Lewis base that can truly trap N2? And this question is still open. We haven't completely solved the puzzle, but I'll share some of our insights with you. So if you look at this as a Lewis base, Lewis acid, that needs to be very reactive, because otherwise it simply cannot react with N2. But similar systems are already known that can react with dihydrogen, and this was developed by Doug Steffen, who also presented his work a few years ago at the PAC symposium in Utrecht. And so what he developed is, can you heterolytically cleave dihydrogen? And so split the bond, get an H plus attached to phosphorus and an H minus attached to boron in this case. And this can be used catalytically as well if you add a substrate like an olefin or a carbonyl compound or an imine that you would like to reduce. And so if you think of this reaction, and if you think of playing billiard, I mean, what is the chance that 3 balls hit each other at the same time? I mean, that chance is virtually 0. And so my point is, if you look at this really nice picture in the article of Doug, then it highlights that the Lewis base should not form the classical Lewis adduct with the Lewis acid. Then the empty orbital and the filled orbital are still available for reactivity. But these two need to come together first, form a reactive pocket, so that then hydrogen can react as a second molecule, if you like. And so that's why I will first focus on steric attraction, so the attraction between these molecules that will allow its subsequent reactivity. And if you think of designing molecules that ultimately can react with N2 or methane, we came across the concept of single electron transfer, where one electron of the donor moves to the acceptor, creating radicals. And so we basically wanted to know the fundamental principles of these two topics that hopefully will allow us to tackle methane and dinitrogen as substrate. So let's focus on steric attraction, because this is a truly important concept in chemistry, and I definitely can recommend this this review by Peter Schreiner. So this is Van der Waals, obviously. This is Peter Schreiner's paper. But if you think of the quadrant model in asymmetric catalysis or the lock and key model in biochemistry, all these models are designed based on steric hindrance. Whereas steric attractions, the attractive forces between molecules, is equally important in terms of selectivity and reactivity. And that's the reason why we also like to focus on this and wrote a review that's called steric attraction, a force to be reckoned with. Now, if we connect this to Lewis acids and Lewis bases, then now I would really like to focus on this green glue that brings together Lewis acid and base, forming a reactive cavity so that the substrate can enter. So we designed molecules, phosphines, boranes, amines, but now with all T-butyl groups attached to maximize the attractive forces, to maximize London dispersion. And in parallel to synthesis, we focused on computational chemistry so that we can have a clear design and a clear notion of which molecules are most important to prepare in the lab. And interestingly, the phosphine-borane combination created the classical Lewis adduct computationally, and experimentally we confirmed this. So there is a considerable energy gain making this adduct, and interestingly, half of the energy can be directly connected to dispersion, so to the attractive forces, to the green glue that holds together these two molecules. If you go from phosphorus to nitrogen, then nitrogen is smaller, so this bond distance is shorter, and actually then these bulky groups, they start to clash into each other. So then steric hindrance takes over, and so for the nitrogen-boron combination, the Lewis adduct is simply not favorable, but the frustrated acid-base combination, so where both Lewis base and Lewis acid are still available for further reactivity, that is the key molecule. That's actually also the one that we would like to characterize fully. And interestingly, the energy gain is a little bit less, but the dispersion is almost equal. And so the attractive forces that held together the adduct as well as the frustrated Lewis pair is almost equal. And that makes sense because the substituents that cause these attractive dispersion forces are also equal. Of course, we went to the lab, but not before computing the acid-base complex, the Van der Waals complex, and the crystallization attempts were very fruitful, very beautiful crystals, but to solve these crystals to date, this has not been able because of severe disorder. And so if you look at the disorder in this molecule, this is basically the only picture that we have. And interestingly, if you look at this, what we could say from the crystal is that the distance from this carbon atom to this central atom is right in between what you would expect of a BC bond and an NC bond. So we could indicate that both are in the crystal. If you dissolve the crystal, then you get both molecules in solution that can be detected by NMR, but we cannot say for sure if it's a borane connected to an amine or that there is a random stacking of these two different molecules. So there's still some work to do. So basically the main option is to reduce symmetry, to make these two molecules a little less identical. And when we make this borane a little bit more electrophilic, then we observe something odd, because these molecules are colorless, and suddenly we started seeing a deep blue color. And by EPR, that can detect radicals, we saw this beautiful spectrum that actually connects very well to this amine radical cation. So where one electron is removed from the amine. And the borane radical anion, we actually did not expect that to be observable because these species are very, very reactive. So we actually postulated that even if these radicals, which are typically reactive, are higher in energy, once they are formed, and if the borate, at least the radical anion, is decomposing, then maybe that can be the reason that the concentration of nitrogen radical cation is increasing. And so if you think again about this central question, how can we make molecules more reactive so that they can actually react with dinitrogen, with methane? We start from a closed shell, donor-acceptor system that is well known for the heterolytic splitting of dihydrogen. But now what we started to observe is this single electron shift from Lewis base to the Lewis acid, creating this radical ion pair. And if you think of the frontier molecular orbitals, it's basically one electron from the donor to the acceptor, and then you have these two separate radicals that in theory, of course, are much more reactive and should be able to attack substrates that are very stable and have, for example, inert CH bonds as in methane. Now, today, or actually before we started, the combination of these two was never observed. Often only the radical cation of the Lewis base. So there was actually little known as how this whole process occurs. So what we did is we simply started looking at the thermochemistry. So how stable is the phosphine borane ground state, if you like? How much energy does it cost to remove an electron? So the electron, the ionization energy to create the phosphine radical cation. What's the energy gain when an electron is added to the borane to create the boron radical anion? And we observed is that this radical ion pair is more than 55 kilocalories per mole higher in energy. So that's if you think of the Boltzmann equation, I mean that state is hardly populated, if at all. So how on earth can you actually make those molecules? And then we realized is that this amount of energy is actually, in the range of the energy that the energy of visible light. So then you can maybe think of doing chemistry not only using thermal energy, using an oil bath or a sand bath, but you can benefit from using light. So and if you think of this donor-acceptor complex, we thought, would it be possible? And by computations, it should, because the LUMO is centered on the borane, and the HOMO is centered on the phosphine, and we even computed a UV vis spectrum where a new band arises from the combination of phosphine and borane. It's actually that van der Waals complex that we aimed at, that actually should be visible in the UV vis, and that's then also called the charge transfer complex. Now, using this theoretical design, obviously we went to the lab, combined phosphine and borane, and lo and behold, we saw color. We saw a charge transfer band in the UV vis, but this color is not from radicals. So this solution is EPR silent. But if you really shine light on this band, so like 500 nanometer wavelength, then you promote the single electron transfer from phosphine to borane, and we could detect this radical ion pair by EPR. So where this is the spectrum, and both radicals are actually available in this EPR spectrum. And so even though it's very high in energy, if you do this experiment at low temperature, using light, you actually can make these radicals. And this came basically to the conclusion of this part that this process is general. It's possible using light to generate highly reactive radical ion pairs. And then, of course, the next step is, what about their reactivity? Reactivity towards hydrogen, methane, N2, and so on. And then we realized, because these radical ion pairs are so high in energy, their lifetime, so we confirmed this spectroscopically, their lifetime is very short. And back electron transfer to the phosphine again occurs very rapidly, and so that the concentration of these species in solution is very, very low. So actually we did a reaction with dihydrogen, and we simply did this reaction in the dark, so no radicals can be formed, and we did that in broad daylight, and we did that using an LED that hits the charge transfer band. We saw no difference in kinetics, and so this really indicates that these radical ion pairs in particular are very short-lived, have then no impact on the reactivity, but of course, and that's now ongoing research, you can tune the redox properties of the donor, you can tune the redox properties of the acceptor, and so we're now working on lowering or reducing the energy difference. So actually, thermally, it should be possible to make these radical ion pairs so that methane and so on is available for reactivity. Now, if you look at this from a concept, this concept of electron transfer in inorganic chemistry is actually known for decades. If you look at this picture, then the molecules I've showed you, donor as a phosphine, acceptor, for example, as the aryl diazonium cation, forms the adduct. And then, of course, it makes you wonder, if we will change the donor, would that directly give access to such a radical ion pair? And using amines instead of phosphines, this is actually possible. It's using a phenyl diazonium cation as a Lewis acid, and basically a simple Lewis base, that it actually does the trick. Because if you do the reaction, you can directly detect the nitrogen radical cation, detected by EPR, and this phenyl N2 radical is formed, is very reactive, rapidly eliminates dinitrogen, and this phenyl radical can then be easily trapped with organic substrates. And this was recently actually published by Burkhard König in Regensburg in Germany, using an organic photo redox catalyst. And we repeated that experiment, but now simply using a toluamine base. And so the concept of using not this two-electron thinking, think of this arrow pushing in organic chemistry, but really these one-electron steps is also very general. And you can apply that to other cations if you like. And so this is the tri-tetraphenyl phosphonium cation. So we basically asked the question, would it be possible to add an electron, get the radical, that then can eliminate not the stable N2, but eliminate the stable triphenylphosphine, so that you can do reactivity reactions with this phenyl radical. And this is actually possible. We confirmed this already in the lab. And now at first you would say, I mean, this is maybe not the most important reaction in chemistry, also solving waste issues. But if you think of the concept using 1 electrons, actually it is. If you, for example, think of the Wittig reaction, so applied for the synthesis of vitamin A, where phosphine oxides are produced in more than 1 million kilograms per year as waste. One of the options is to convert it to this chlorophosphonium cation. And then industry, this is actually the synthesis that is applied by BASF. Now, if you think again as a phosphonium cation, we asked ourselves the question, do you need aluminum, or do you simply need 1 electron? Just add an electron, make a radical, and this radical is very unstable. The PCl bond is the weakest, so this will simply homolytically cleave. The chlorine radical eliminates, and then you get the triphenylphosphine back, which you can use again for the Wittig reaction. And this is something we're working on, and we already confirmed this. That not aluminum as a metal is needed, but simply only 1 of its electrons in this reduction step. Now, if I would zoom out and look at the entire phosphorus chemical industry, many vitamin A synthesis, of course, a small part. But how is, for example, triphenylphosphine made? It comes from phosphate rock, so a fossil resource. Then the phosphorus element is created in a highly energy-intensive process. Then PCl3 is created, so addition of chlorine gas, and then you can add sodium metal and chlorobenzene, and then you get triphenylphosphine. And this is, of course, important to sustain and promote circularity, and actually we do that for a wide variety of applications, really improving the current synthesis of chemistry in the industry. But where can you have the biggest impact? That's over here. More than 90% of phosphate goes to phosphoric acid. And simply adding sulfuric acid, and so that's the combination of phosphorus, or the link of phosphorus with sulfur. Sulfur, by the way, coming from the oil production as a byproduct. So this phosphorus-sulfur combination is easy, or is important to make phosphoric acid, which is the building block for fertilizers, feed, and food additives. So this step is also the cause of this entering the environment. And for nitrogen, it's the Haber-Bosch process, where ammonia and phosphoric acid-based compounds are used as fertilizers, feed, and food additives, but afterwards enter the environment. So how can we tackle this? Of course, the starting point for phosphorus chemistry is this beautiful synthesis by Hennig Brandt, where he reduced liters and liters of urine containing phosphates, and he produced for the first time phosphorus, the element. And I really like this experiment. Not only it's the discovery of the element phosphorus, but it's actually the discovery of that element using waste as resource, using phosphate waste from urine. Now, of course, after the discovery in the alchemy, we went to the mines, phosphate mines. There is plenty. There still is, at least for a few years. But as a consequence of our linear thinking, there is also an abundance of waste in the environment now. And that is generating this green chemistry. It's a green of algae growth due to an excess of nutrients, in the ocean where it's in this amount should not be. So can we actually solve this environmental issue and generate resources at the same time? And this is possible. And one of the options is, if you think of phosphate and ammonia in water, both are soluble. One option is to add a metal like magnesium, where a magnesium ammonium phosphate is formed that is insoluble. So then you basically can remove these essential elements from the environment. But then, of course, the next step to do something useful with it is still needed. And that's actually what we developed in the past years. We developed a process that can use phosphate waste as resource. And we produce, for example, monoammonium phosphate, a specialty fertilizer. And currently, this monoammonium phosphate is prepared from ammonia from the Haber-Bosch process, phosphate from the mine, and we basically prepared it from waste. And we also developed a process that actually recovers the magnesium, which is not in the product, so that the magnesium can be reused for Slootweg production. And a few years ago, we started developing this in Amsterdam using first an NMR tube, and now SESFOS, our spin-off company, is actually realizing this on a pilot plant scale. So I'm really looking forward seeing the product come out of this reactor, hopefully in a few months. And so the concept is really use waste as resource, products that are not used anymore, and convert that to new products. And of course, develop the chemistry that is needed, that starts from renewable resources, that ends with renewable products that you can ideally mine locally. And of course, that you need to convert waste or product into new products using chemistry that also contributes to the concept of benign by design. And so in this fashion, chemistry truly has a large impact on society, and then of course tremendously contributing to our global sustainability goals. And so with this, of course, would like to thank the PAC Symposium organization. I think you've done a tremendous job. And I also would like to thank my group. And it's really a pleasure working in the Van Hoff Institute for Molecular Science. But for this occasion, we gathered around Van der Waals of the Physics Institute in Amsterdam, because we also needed his force to do the chemistry we like. So with that, I would like to end and again highlight that chemistry truly can impact the development of a more sustainable society.